So let's talk about the energy of an oscillation. So we got a mass on a spring. So here is the equilibrium spot. If it's away from the equilibrium spot here, so it's some distance x over. If x is positive, the force is negative. If x is negative, the force is positive. So this is what we call a restoring force. All right. So we can look at it and say, well, there's a couple of things that we can say. We know that the total energy is going to be kinetic energy plus potential energy. And so we know that for a spring here, that kinetic is going to be 1/2 mv squared and potential is going to be 1/2 kx squared. We also know that when this is at its extreme, so when x equals a, the amplitude, then it momentarily stops. So the velocity is 0. And so that means that the kinetic energy, 1/2 mv squared, and u equals 1/2 kx squared, the total energy is going to be k plus u. So when you are at x equals 0, so that's going to be the equilibrium spot. Potential energy is 0, and the kinetic energy is at its max. On the other hand, if you are at the extremes, so x equals a, then the velocity is 0, so kinetic energy is 0, and potential energy is at max. So that would say that the maximum kinetic energy equals the maximum potential energy. So that's one introduction here to this. So that's one thing. The other thing is that at any particular moment in time, then kinetic plus potential is going to be the total energy. Okay, well, if x is some a cosine omega t, then v is going to be minus a omega sine omega t. So if you were graphing this, then if x looks something like that, so that's x, then a would look something, a would be minus sine, so that would be something that would look like this. So that would be the v. Okay. So total energy is 1/2 mv squared plus 1/2 kx squared. So that would be 1/2 m times a squared omega squared sine squared omega t plus 1/2 k a squared cosine squared omega t. Well, we know that omega is square root k over m, so omega squared is k over m. If I plug that into this equation up here, okay, then we could then say, therefore, that the total energy is going to be 1/2 m a squared k over m sine squared omega t plus 1/2 k a squared cosine squared omega t. Okay. Well, that m cancels that. Okay. And so we can factor out 1/2 k, they both have k, they both have a squared, and then they have sine squared omega t plus cosine squared omega t. But we know that sine squared plus cosine squared is 1. So the total energy equals 1/2 ka squared. So what that means is, as this harmonic oscillator is vibrating, if you add more energy, it vibrates bigger, but notice that the period 2 pi square root m over k does not depend on that. Only the amplitude is related to the energy. So you add more energy, it does not oscillate faster. In other words, the period doesn't change, only the amplitude changes. Now this actually turns out to be a really interesting thing, because if we have an object right here and it's made up of a whole bunch of molecules, then all these molecules are interacting with each other in such a way that if one molecule gets out of position, the other molecules pull back on it. It's roughly a linear restoring force. That's why stress and strain is linear. Okay, well, that means that this restoring force, if the molecules are vibrating a little bit, well, think about it, that's thermal energy. More thermal energy, the higher the temperature, the more the molecules vibrate. And so that means that if you add energy to it, each molecule vibrates and the amplitude of the vibration is bigger, and so that means that this object will expand. Okay, so this is why, for example, that the change in length of something, depends on the original length times some coefficient times the change in temperature. Okay, and so in this case, T is for temperature, not period. But the change in temperature corresponds to is related to the change in thermal energy. This is a constant, the constant of linear expansion, and bigger L means there's more molecules. And so that means if you're twice as long, you get twice as many molecules, each one taking more space, and so you end up with twice the change in length. And so now we're able to start correlating thermodynamics with molecular motion. So that's an extension to this whole concept.